In this lesson, we are going to explore how to create an exponential model that fits the data that we are given for a real-world scenario. So, first, before we start looking at the investigation, let's first take into consideration the information that we need to know in order to come up with an exponential model that represents a scenario. So in the warm-up, it says, over the last 10 years, Victoria Julian has been collecting data on changes in median house prices in her area. She plans to buy a house 5 years from now and wants to know how much money she needs to save each month toward the down payment. First question is, how can she make an intelligent prediction of what a house might cost in the future? So if you think about this, the first thing that she would need to know is, how are house prices changing? Okay, so she would want to know a rate of change. And if you think about this, this is typically going to be a percentage. So house prices are going to increase a certain percent each year. And so when it is increasing by a certain percent each year based off of the value of the house, then this is going to turn into an exponential equation, because the amount that it increases each year is not going to be the same. So it's going to increase by a different amount each year. Now, the other thing that she would have to assume is that, the house prices increase by the same percent each year. So if there are things that might affect this, like COVID, there might be some outliers in her data, which could cause a slight difference in her prediction of what a house might cost. So what we're going to do is we're going to take a look at an example. So in real world situations like population growth, price inflation, that means the increasing of house prices, the decay of substances, this is all going to be things that are typically going to be exponential over time. And what we want to do is talk about how to find the exponential model for this type of data. So the example that we're going to first take a look at specifically looks at radioactive decay. And what radioactive decay is it's how particles in the air, or let's say radiation, like nuclear particles, it's over a period of time that element is going to break down and decay. And when they break down and they become different elements and become less harmful, this is what we call radioactive decay. So what we did in class is we took a simulation right here, and we took this simulation and we put 200 particles or 200 atoms into the atmosphere right here. And then what we did was we let some time pass, and as time passed, we watched the particles move around, and then they stopped. And when they stopped, the particles that were in this red zone were particles that had decayed, and they were no longer in our system. So after we took the particles that decayed out, we had a certain number of particles remaining. Then we let some more time pass, and then we stopped it and counted the number of particles that decayed, and then we took those out, and then we continued this process until there were less than 10 atoms left in the atmosphere. And so what this looked like on our table was this. So go ahead and write these down. So we started with 200 atoms of our element, and then after 1 year, there were only 142 atoms remaining. After the second year, there were only 98 atoms remaining. Third year, 67, and so forth. And finally, once we got to the 8th year, there were only 9 atoms remaining. So at that point, we stopped. So then what we want to know, because again, remember when we were talking about the warm-up, we need to know our rate of change. And we know that in exponential functions, our rate of change is going to be equal to our successive ratio. Okay, remember by successive ratio, another word for that is our constant multiplier. Okay, and so we want to figure out our successive ratio for each of these cases. So we would do that by taking 142 dividing by 200. So 142 divided by 200, that would give us 0.71. Then you have 98 divided by 142, and that would give us 0.69. And then you have 67 divided by 98, that would be 0.68. 43 divided by 67, that would be 0.64. Then you have 27 divided by 43, and I'm rounding these, that'd be 0.63. And then we have 16 divided by 27, that'd be 0.59, then 0.75, and 0.75. And so the question here is, how do these ratios compare? And so if you look at this, you'll notice that all of these ratios, they're pretty close together. You might have this one little one that's a little bit of an outlier. Maybe these ones might be, they're a little bit different. But for the most part, they're all falling in between that high 0.6 to 0.7 range. So if we take a look at that, we come down here and we ask ourselves, well, which of these ratios would be the correct one to use to represent our rate of change? And the answer is, you could choose one, or what we could do is we could find the average of our successive ratios. So choose one representative ratio. We're going to choose our average of the successive ratios. And that comes out to be 0.68. So if we find the average of all of these numbers, it comes out to be 0.68. So the next question is, at what rate did your atoms decay? So we know that our constant multiplier is 0.68. So when we want to know our rate, we want to know at what rate is are these atoms disappearing. So 0.68 is our constant multiplier. Okay. Now typically we'd say that our constant multiplier is b when we're talking about exponential equations, but when we're talking about exponential growth and exponential decay equations, b can be rewritten as either 1 plus r or 1 minus r. And in this case, because we're talking about exponential decay, we're going to use 1 minus r. So we have 1 minus r is equal to 0.68. Now we want to solve for r. So I'm going to subtract 1 from both sides. We get negative r equals negative 0.32. And then if we multiply both sides by negative 1, we get r equals 0.32. So our rate would be 32%, which means that 32% of the atoms are decaying each year. So if we wanted to take that and write an exponential equation that models this relationship, we could either write y equals our initial amount, which was 200, times 1 minus 0.32 to the x power, or you could write y equals 200 times times 0.68 to the x power. 0.68 was the average of our successive ratios, and it's also 1 minus 0.32. So either one of those equations work. Now, if we wanted to see how well this equation represented this data, what we would need to do is we would need to plot our data on Desmos. And so if we do that, have it right here, we have all of our data from our simulation, and if we type in our equation, y equals 200 times 1 minus 0.32 raised to the x power, you'll see that that green line does in fact represent that data fairly well. You could also see y equals 200 times 0.68 to the x power, so you can see that those are the same equations. So in step 9, it asks how well does it fit the data? It represents it pretty well. And another way that you could figure this out, okay, so I'm going to show you how to have Desmos solve or find an equation for you, is you could type into your equation or into your Desmos line, y sub 1 is approximately ab raised to the x sub 1 power. And you'll see that it gives you an equation. Now, one thing to pay attention to is that the starting value that it's going to give you might be a little bit different than what we are starting with. So you always want to use the starting value from our problem. But what it does tell you is it tells you the value of b right here, 0.68, which, if you remember, is the exact same value for b that we got by looking at our successive ratios. So a quick way to find out your successive ratios is to type your data into Desmos and then type in this exponential approximation, and then it will tell you what b is. So you can do that whenever I don't tell you that you need to do it by hand. Now, let's skip over step 10. So what we're going to do is we're going to take a look at this example. So again, we need to find a model that fits the data. In order to do that, you would need to find the successive ratios and then find the average of those successive ratios. So you would have to do 277 divided by 262. And that would give you a successive ratio of 1.057. Then you'd have 294 divided by 277. That would give you 1.061. And then you would keep going. Okay, so after and we'll do one more. 311 divided by 294. That would give you 1.057. And then, or actually, it'll give you 1.058 if you round. So after you go through and find all of these successive ratios, you would add them all together and get a number, and then divide by 12, because that is how many successive ratios you would have to find the average of. Now, a quicker way to do that is to type this table into Desmos, and again, that's what we'll do right here. So we would take this and type into Desmos right here. We would have table, and then we have 0, 1, all the way up to 12. And then for 0, we had 262, and then 277, 294, 311, 330, 349, 370, 392, 415, 440, 466, 494, and 523. And you'll notice you can't see our points, but if we hit this little zoom fit button, it will show us our points. And then we're going to use Desmos to find out our value for b. Right there. And you'll notice you get a curve of best fit that passes through those points pretty well. And if you scroll down, you'll see that b is equal to 1.059. So if we wanted to write an equation for a model that fits our equation, we'd have y equals, we're not going to use their a value, we're going to use what the problem told us, 262. Then we have parenthesis 1.059 raised to the x power. And you'll see that purple line that pops up is pretty much the same as the black line. So if we wanted to find a model that fits the data, again, 262 times 1.059 to the x power. Now, adding one small question onto here, it asks, let's say, what if I asked you, first of all, is this growth or decay? And we know it's growth because because this is bigger than 1. Okay, and so since this is growth, if I asked you what is the growth rate, you would take 1 plus r is equal to 1.059, subtract 1, and get r is equal to 0.059. And then for the percentage, you would say that is 5.9%. So it has a growth rate of 5.9%. Now, in part B, it asks us to find the frequency for two more notes, note 24 and note -12. So to do that, we would just take our equation, y equals 262 times 1.059 to the 24th power, y equals 262 times 1.059 to the -12th power, and that would give us 132 hertz for this one, and 1030 hertz for the second equation, or for that first one. Now, the question The next question says, is there a note on this piano with a frequency of 800 hertz? So there's several ways that we could figure this out on Desmos. So the first way that we could figure this out is we could type in to this. We have our equation that represents the model, and then we could type in y equals 800. And if we do that, and we zoom out a little bit, you can see that those two lines intersect at one point, which means that this is our solution. So it says note 19.4 would have a frequency of 800 hertz. So what that means, so we'll put note. So it first asks, is there a note on this piano with a frequency of 800 hertz? The answer would be no, because 800 hertz occurs when x equals 19.4, and that is between note 19 and 20. There is no note 19.4, so therefore this note does not exist, because notes come in whole numbers. So that being said, that is how you would find that value. Now, if we take a look at the summary questions, it says, how do you know what base to use for an exponential equation representing data? What we would do here is we would just find the average of successive ratios. So find the average of your successive ratios, and then that would be your base for your exponential equation. Then it says, how can a graph of the data help you find an exponential equation that fits? You can adjust A and R to help it fit, to help the line fit. Okay. And again, how do you make an exponential graph steeper or shallower? You adjust A or R. Or you adjust R. Okay. So if you look at this, it says rewrite each value as either 1 plus R or 1 minus R. So what you would do here is, this is growth because it's bigger than 1. So you would use 1 plus R equals 1.25. And then that would give you, if you subtract 1, R is equal to 0.25. So that rate of increase would be a rate of increase by 25%. And then if you take a look at the second one, it's decay. So 1 minus R is 0.80. Subtract 1, you get R is equal to negative 0.20, or negative R is equal to negative 0.20. That gives you R is equal to 0.20. And so that's going to be decreasing by 20%. Okay. And then you can go ahead and look at the examples 2 and 3, and now go ahead and begin working on your homework. And if you have any questions, message me on Marind, email me, or feel free to ask questions the next day in class.